Just to get a feeling for how the polar equation for a conic section works, let's play around with it a little bit in GeoGebra. So here I have GeoGebra set up to have I've called the origin F, so that's going to be the one focus of our conic section. And then I have this vertical line L, this is our directrix, and I have it set up so that I can drag this around by dragging this point to the right and to the left. And I've asked GeoGebra to plot a graph of this equation, r equals e times d over 1 plus e cosine theta. Now remember, this is the polar version of the equation that produced our conic section. E is the eccentricity, and that's a real number that we choose ahead of time. And I have a slider here that lets me control E. D is the distance from F to the from the focus to the directrix, and right now that's 2. Okay, you can see that D is 2 right now, and I can change D by dragging the directrix around. And the definition for the polar definition for this conic section is that the distance from F to P over the distance from, this should be the distance from F to P over the distance from P to L. Let me fix this. This should be a P. So the distance from F to P over the distance from P to L should be equal to the eccentricity. And you can see that this is 0.79. It's the eccentricity. So the polar version of the equation is r equals ed over 1 plus e cosine theta. And then this here is just putting in the values for e and d that we have. So if you remember back to when we talked about ellipses, the eccentricity controls the general shape of the ellipse. So a smaller eccentricity gives you a rounder ellipse, and a larger eccentricity gives you a pointier ellipse. And we can see that happening. So if we decrease the eccentricity, that the resulting conic section is getting rounder. It's also getting smaller, but it is getting rounder. As we make the eccentricity grow larger and larger, we get an ellipse that is much longer than it is tall. And the larger we make the eccentricity, the more extreme the difference is between the length of the ellipse and the height of this ellipse. Now remember, when we make the eccentricity 1, we should get a parabola. And if I very carefully move this slider there, now we have a parabola. It's actually, a parabola looks very similar to these nearby ellipses that have very large eccentricity. So it's actually hard to tell that this is a parabola and not just an extremely large ellipse. But it is a parabola. When the eccentricity gets larger than 1, we know we get a hyperbola. So if we bump the eccentricity up just a little bit more, now it's a hyperbola. Of course, it's hard to distinguish a hyperbola with very small eccentricity from a parabola. But if we make the eccentricity larger, you'll be able to see that this is indeed a hyperbola. We are forming some asymptotes here. Okay. Now, if the eccentricity gets big enough, then we get the other half of the hyperbola. You might have wondered, oh, wasn't the other half missing? No, it was just off the right-hand side of the screen. Once the eccentricity gets big enough, the right-hand part of the hyperbola gets close enough to everything else that we can actually see it. So that's the effect of changing the eccentricity. Notice that when the eccentricity is bigger than 1, we get a hyperbola, and when it's given that we have a hyperbola, when the eccentricity is larger, we get a hyperbola that opens wider, and when the eccentricity is smaller, closer to 1, we get a hyperbola that opens more narrowly, like this. Okay, so that's the effect of changing the eccentricity. So what about the effect of changing d? Well, if you look at our expression for r here, r equals e times d over 1 plus e cosine theta, this is, try to isolate the effect of d here. This is just d times e over 1 plus e cosine theta. So it seems like what changing d should do is just scale up r according to whatever d is. And that should just make this whole thing bigger or smaller without changing its general shape. And when I say general shape, what I mean is sort of the relative width and height of this ellipse. So let's try changing d to see how that works. So if we make this larger, the ratio of the width to the height of this ellipse looks like it's pretty much staying the same. That's just another way of saying the eccentricity of the ellipse is staying the same. But the general size of the ellipse is what's changing. Okay, if we switch to the parabola with eccentricity 1, this is indeed all the same parabola. It looks like maybe the parabola is opening wider or more narrowly, depending on where we put the directrix. But in fact, every parabola is the same parabola, it's just you're zooming in different amounts. So making the parabola open more widely like this is the same as zooming in on the parabola that we started with. In other words, it's just scaling the parabola up, which is what we said d should do. If we switch to a hyperbola, you can see that moving d doesn't change the sort of general proportion of this hyperbola, it just zooms us in or out of this hyperbola. Okay, maybe the last thing to check on with this picture is that the distance from our point P to the focus is really just the eccentricity times the distance from P to the directrix. So let me show those distances. So there's the distance from the point to the focus, and here's the distance from the point to the directrix. And down here, or up here, is a label that we'll keep track of. On the left-hand side, it's the distance from the point to the focus. And on the right-hand side, it's the eccentricity times the distance from the point to the directrix. It's a little hard to tell if this calculation is right. But if we change the eccentricity to something nice, like say 1/2, and let me make this a little bigger. Okay, so now you can see that, yes, this the distance from the point to the focus, which is on the left here, really is 1/2 of the distance from the point to the directrix. And even if I move this point around this ellipse, these distances change, but they change in sync so that one is always 1/2 of the other. Even if I'm on this side of the hyperbola, or ellipse, this side of the ellipse, no matter where I am on the ellipse. If I change the eccentricity to say, I don't know, 0.9 maybe, the ratio between these distances is different. Now they're much closer because we're multiplying 1 by 0.9 instead of by 0.5. So the ratio between the distances is different now than it was before, but still the ratio of distances is a constant. This is true even if we switch to a hyperbola. So now the ratio of distances, now the distance to the directrix is the small one instead of the big one, and the distance to the focus is the big one instead of the small one. And you can see no matter where we move this point on this hyperbola, this equation between these distances related by this eccentricity is always true, even if we pop the point over to the left-hand side of the hyperbola.